The AC primary current produces an alternating flux in the core. Most of this changing flux gets linked with the secondary winding through the core. The varying flux will induce voltage into the secondary winding according to Faraday's law, that is the electromagnetic induction. Voltage level change, but frequency, time period, they remain the same. That is one of the very big advantage of the transformers. So you can see here, so the voltage level is changing. You can step up or step down, but this frequency or the time period or frequency, both are same, right? So F is T is equal to 1 by F, or F is equal to 1 by T, the same. So the frequency is not changing at the output. So that is good for us in many applications, especially in the power stations. So we either it's a hydro power station or thermal power station or atomic power station, we produce high voltage. We want to transfer the voltage from the station which is producing the electricity to the distribution station. From the distribution station, they are distributing to different homes and industries, right? So we need to transfer the voltage in different levels, but the frequency should not be changed. For example, we are using in Norway 50 hertz. So 50 hertz. So it should maintain from the time they produce the electricity until it reach our home. And also you should remember there is no electrical contact between these two windings. These are isolated, and electrical energy gets transformed from primary to the secondary in terms of magnetic flux. Okay, so now we will just go to this mathematics part or some equations part. So we already know transformer means we have the primary winding and we have the secondary winding. The voltage induced in the primary, it's called V1, or you can also call EP. It's the same EMF in the primary. And similarly, we also have the E2, that is the induced EMF in the secondary winding. So this is ES. And this is also called V2. And N1 and N2 is the number of turns. So you can change the number of turns and you can make step up or step down. And this two ends of the secondary winding is connected directly to the load. Okay, so now we will see the equation. So equation, it means like voltage induced in this primary winding is equal to N1 times F times pi max. So N1 is the turns, F is the frequency. For example, in Norway, it's 50 hertz, and pi max, that is the magnetic flux because of this applied voltage. And V2 is the same. Everything is the same, just we are using the different number or label to indicate this is from the secondary winding, the number of turns in the secondary winding. So now we can just make the ratio. V1 divided by V2 is equal to, I put the same equations here. This is the equation 1 and this is the equation 2. So equation 1 divided by equation 2. So what will happen now? The flux is the same flux. So I'm just canceling this. Similarly, frequency is also the same. I'm canceling these frequencies. So finally, I get this equation. V1 divided by V2 is equal to N1 divided by N2. This is one of the very important and very easy equation to remember. So this is the voltage relationship for ideal transformers. So already you know what is V1, what is V2. Similarly, what is N1 and what is N2. So now, based on this equation, you can easily find the induced voltage in the secondary winding, right? V2. So if I want to have V2, then what should I do? So here you can see this equation. So V2 can go here. The N1 by N2 can come to this side. That will be N2 divided by N1. So N2 divided by N1 times V1, right? So this is just a very simple equation transformation. So N2 is equal to V1 will be as it is times N2 by N1, because it comes to the opposite side. So we have to flip it. So this is the equation it's given here. Sorry, this is V2, not N2. V2 is equal to V1 times N2 divided by N1. Okay, this is one of the important equations, try to remember. So if you know the number of turns in both windings, And if you know the applied voltage, then you can easily find the induced voltage in the secondary winding. So V2 is equal to V1 times N2 over N1. Okay, so ideal transformers, this is again the same thing. Here what we have found in the previous slide, voltage relationship with respect to number of turns. So now here we are finding turns ratio. Turns ratio, the same actually, N1 divided by N2. So we use the label, new label, it's called A, small a. So A is equal to V1 over V2 is equal to N1 over N2. So the V1, and we can also call this as a VP or EP, that's not a matter. So please remember this formula also. This is the turns ratio, the same formula actually, what we had seen here. We are just putting A here, that's all. And as I said, you can step up or step down the voltages in the secondary side by varying this N2 value. It means you can increase the number of turns in the secondary winding, or you can decrease the number of turns in the secondary winding. If N2 is greater than N1, then it's called step up transformer. N2 is greater. It means like a number of turns are more here. For example, we have 500 turns. Here we have 1000 turns. So it means you can get more induced EMF this side. So you are stepping up the voltage. And similarly, N2 can also be less than N1. So in that case, for example, it will be the opposite. Maybe let's say this is 500, right? Instead of 1000 here, we have just 250. Then it means the voltage induced in the secondary winding will be much lesser than the primary side. So we can also step down. So based on the N2 and N1 value, we can step up or step down the secondary voltages. And for ideal transformers, so this is the same formula. I repeat in each slide because we are going to use this in the problems now. So A is equal to V1 divided by V2, V1 divided by V2, and also N1 divided by N2. And okay, for further simplifications in the problems, I will consider V1 as a EP, V2 as a ES. It means EMF induced in the primary and EMF induced in the secondary winding. Similarly, number of turns in the primary winding, number of turns in the secondary winding. So this is going to be NP and this is going to be NS. Similarly, this is going to be VP and the other side is going to be VS. Okay, so now we will move on. So now you know what is the turns ratio. Turns ratio A is equal to N1 divided by N2. Now we are calling NP divided by NS, EP divided by ES. So now if you want to find the voltage in the primary winding, EP is equal to A times ES, right? Just you are bringing the ES here. So this is also the turns ratio is a scalar because by changing the turns ratio, you can scale up or scale down. So you can introduce the phase shift or the control the induced EMF in the secondary side. And apparent power balance. Okay, we know power balance. P is equal to VI. This is the very basic equation. So the same equation we are writing here like this. So primary side is EP times IP. It means like a VP IP. So we are indicating V as a E. So EP times IP is equal to ES times IS. So we are equating because power in the primary side is equal to power in the secondary side. Okay, then we can also simply say instead of power as a P, we are saying here yes, because we are using P. The letter P is for the primary notation. So instead of using the power as a P, here we are using yes. So yes suffix P is equal to yes suffix S. As I said, the induced EMF or the magnetic flux in this primary winding is equal in the secondary winding because of this magnetic core. So it means the power in the primary side is also equal to the power in the secondary side for ideal transformers. We are talking about the ideal transformers. Okay, so it means no power losses in this ideal transformer. So now we can also make the current ratio. Current ratio is IP divided by IS is equal to 1 divided by A. So, but you should remember these two equations now. VP divided by VS is equal to NP divided by NS, that is A. But similarly, IP divided by IS is equal to 1 divided by A. You can see here is opposite. A is reciprocal now. It's not the same. IP divided by IS is equal to 1 divided by A. So whenever we talk in terms of voltages, it's just equal to the turns ratio. Whenever we talk in terms of current, it's 1 divided by A. Okay, so current ratio is the inverse of the voltage ratio. Okay, so now we will see again one more thing, how to calculate the impedance in both sides. In input side, we have some impedance that is called input impedance. Output side, the load side also we have the impedance that is called load impedance. So normally we know V is equal to IR, Ohm's law. So R is equal to V by V divided by I. This is the general formula. We all know that very well. So this R can be an impedance actually. V is equal to IZ. That is what we have mentioned here. So Z load is equal to, load impedance is equal to the voltage in the secondary side divided by the current, right? Voltage divided by current. So voltage is ES and the current is IS. Secondary side voltage divided by secondary side current. This is the load impedance. Similarly, input impedance is equal to the voltage in the primary side divided by current in the primary side. So now we know the basic equation for impedance in both sides. So now we will rewrite this equation in different way. So we already, in the previous slide, I already mentioned about the turns ratio. A is equal to primary voltage divided by secondary voltage, EP divided by ES. Of course, NP divided by NS. We are writing in terms of voltage. Now we are writing the turns ratio in terms of current. So IP divided by IS, primary current divided by secondary current is equal to 1 divided by A. So we know these two equations we had seen just before. So I rewrite this equation this way. So ES is going up here, A is coming down. So ES is equal to EP divided by A. This is one equation. And similarly, here we have the IS. So now I want to keep this IS. I want to bring the IS up and then the A up here. So IS is equal to A times IP. Right? So now I found the equation. ES and IS means what? The voltage induced in the secondary winding, current induced in the secondary winding. So voltage and current in the secondary side, IS and ES. So I write this ES and IS in terms of primary values. So primary side, I have the EP and IP. So now I am writing the same. ES is equal to EP divided by A. IS is equal to A times IP. So why I am doing this? You can see here now. We already know load impedance is equal to AS divided by IS, right? This is, let us say, this is equation 1. And this is equation 2. And this is equation 3. So what I am going to do, I am going to apply the equation 2 and 3 in equation 1. So ES divided by IS, this equation, this is nothing but Z load. Z load. And ES means what? That is EP divided by A. And IS means what? A times IP. So I can just rewrite this EP divided by A. So finally I will get like this. EP divided by IP times 1 divided by A square. So this is the final equation for Z load. So now EP by IP is what? EP by IP, EP divided by IP is nothing but input impedance, right? This is input impedance. So Z in, So I replace this one. Let us say now equation number 4. This is equation number 4. And this is equation number 5. So I am going to apply equation number 4 into this equation number 5. So apply 4 into 5. Apply equation 4 into 5. So what will happen now? So Z load is equal to Z in times 1 divided by A square. This is the final equation. This is the final equation now we found for Z load. So Z load is the load impedance. So we are just going step by step. We know the basic equation for the impedance based on the Ohm's law. And we know this turns ratio in terms of voltage and in terms of current. So I am just rewriting this same. This is the very basic equation. I am writing in terms of secondary voltage and secondary current. This equation becomes like this, and this equation becomes like this. And I am using this equation. I am applying these things here, and then I am just simplifying, and finally I get Z load is equal to Z in times 1 divided by A square. So this is the final equation. And of course, if you want to find only input impedance, then keep this Z in this side, bring this A square to this side. Then that is called Z in is equal to Z load times A square. Of course, you can write in so many different ways the same equation. So that's not a matter. So this is one of the important equations, remember. So now we are looking at the load impedance seen from the primary side. So that is, it means we are applying everything in terms of primary side values, EP and IP is here. And we find the impedance value like this. Okay, so now the same, now we will find, now we are looking at the impedance from the secondary side. You can see here, now we are looking from the secondary side. Here in the previous slide, we are looking from primary side. Now we are looking from the secondary side. So again, the same thing. We know the basic equation, turns ratio in terms of voltage and in terms current ratio in terms of number of turns, or turns ratio in terms of voltage, turns ratio in terms of current. And I am rewriting this equation now with respect to primary values or primary winding side. EP is equal to A times ES. IP is equal to, now you can see 1 divided by A times IS, that is IS divided by A. So now I have two equations based on these basic two equations. We already know the input impedance means Z in is equal to ES by IS. Actually, it's supposed to be EP divided by IP, right? But now we are looking from the secondary side, the impedance values. So let us say here, Z load is equal to EP divided by IP. So now I am going to replace this. This is equation here. Let us say this is equation 1 and this is equation 2. So we are going, this is equation 3. So we are going to apply this equation 1 and 2 into this equation. So EP is what? A times ES, A times ES. And here we have the IS divided by A, IS divided by A. I'm applying instead of IP. So I am just simplifying again. Then I will get, you can see the simplification is also very easy. So IS divided by A, when it becomes multiplication, it's going the opposite. So A divided by IS, IS is becoming A divided by IS. So now if I make, what will happen? ES divided by IS times A square. So that is what written here. So what is this? This is called Z load. Z load is equal to Z in times this ES by IS. ES by IS right now, it's called Z in. So Z in. So we are writing like this, Z in times A square. So now we know what is the formula for load impedance when we look at, or when we view from the secondary side, this is the secondary side. So now we found two formulas. And similarly, if you want to find only the input impedance, then you have to bring this A to this left side. So Z in is equal to Z load divided by A square. So now we found two equations for the same load impedance and input impedance. So here you can see, so Z load is equal to Z in divided by A square. Okay, we forget this side. We will just only remember in terms of Z load. Z load is equal to Z in divided by A square. We are dividing the number of turns square. But in the second slide, Z load is equal to Z in multiplied by A square. So now we have two conclusions. So for load impedance, moving from primary to secondary, it's divided by A square. So please keep this one in the mind, because we need this for the problems now. And similarly, we are moving the impedance from secondary to primary side, because we know the transformer we can look at from primary to secondary, similarly from secondary to primary. So that is why now we found two equations. Z load is equal to, here in the from primary to secondary means divided by A square. So input impedance divided by A square. Similarly, for when you look at from the secondary side, then you have to multiply by A square. Multiply what? Multiply the input impedance. So Z load is equal to Z in multiplied by A square. So these two equations, try to remember.